Hey everyone, welcome. Today, we're not just going to learn about physics. We are going to become rocket engineers. That's right. We're going to build and race our very own balloon-powered cars to really get a feel for one of the most powerful laws in the universe. So, you ready to get building? Let's do this. Just look at that. An absolutely massive rocket blasting off, defying gravity, and heading for the stars. It's an incredible sight, isn't it? But all of that power, all of that engineering, it all boils down to one simple little question. So, what is it? I mean, really, what is pushing that thing sky high? A lot of people guess that the rocket pushes off the ground, but think about it. It keeps going up and up long after it's left the launch pad. The real secret? Well, it's a law of motion figured out by Sir Isaac Newton more than 300 years ago. And that is exactly what we're going to explore today. So here's our game plan. First, we're going to uncover that secret to motion. Then, it's time to get our hands dirty and build our rocket racers. After that, we'll test them out, figure out how to improve them, check what we've learned with a quick pop quiz, and finally, we'll analyze our results just like real scientists. Let's get to it. All right, Section 1. Action-reaction, the secret to motion. This is it. This is the big idea, the core principle that makes our little racers and those giant rockets actually go. And here it is. Simple, elegant, and incredibly powerful. Newton's third law of motion. You've probably heard it before. For every action, there is an equal and opposite reaction. It's short, it's sweet, and you know what? It explains so much about how literally everything in our world works. So, let's unpack that a little. What it's really saying is that forces never act alone. They're always part of an interaction, kind of like a push and pull dance between two objects. You can't just push on a wall without that wall pushing back on you. Forces always, and I mean always, come in pairs. And you can see this idea everywhere you look. Check out these examples. A car tire pushes the road backward, and the road pushes the tire forward. That's what moves the car. A rocket shoots hot gas down, and the gas pushes the rocket up. See? It's the same pattern over and over again. Every single interaction has this pair of forces. And there's a name for this. It's called a force pair. Let's break this down because every part is important. The two forces are equal in size, they're opposite in direction, and here's the absolute key. They act on two different objects. Don't forget that part. Okay, so this brings up a really common question. If the forces are equal and opposite, why doesn't everything just, cancel out? Why does anything move at all? Well, look on the left. With our racer, the forces act on different things. The balloon pushes the air pushes the balloon. Since they're on different objects, they can't cancel. But now look at the book on the right. Those are balanced forces. Gravity and the table are both pushing on the same object, the book, so they do cancel out. That's the huge difference. All right, enough theory. Talk is cheap, right? It's time to actually put this into practice. Let's get our engineering hats on and build our very own rocket racers. Your mission, should you choose to accept it, is to build a vehicle powered by Newton's third law. Here's the gear you're going to need. Go ahead and grab a styrofoam tray, a couple of plastic stirrers, those are for your axles, 3 of those bendy straws, a balloon, some tape, scissors, and a ruler. This is your official rocket scientist toolkit for the day. So, here's a quick bird's eye view of the whole process. We're going to walk through this step by step, don't worry, but this gives you a pretty good idea of how all these simple little pieces are about to come together to make something awesome. Okay, let's do this. Step 1, carefully cut out the body of your racer and 4 wheels from the styrofoam. Step 2, poke a nice clean hole right in the center of each wheel, and then push the stirrers through to make your axles. Step 3, tape 2 small pieces of straw to the bottom of the racer's body. These are going to hold your axles in place. Step 4, just slide your wheel and axle sets right through those straws. See? Easy. Step 5, let's build the engine. Tightly tape a straw to the opening of the balloon to make a nozzle. And finally, step 6, mount your balloon on top of the racer, making sure that straw is pointing straight back. And just like that, you have a rocket racer. And now for my favorite part. Building the racer is cool, but testing it, that's where the real science begins. It's time to move into the experimental phase. Time to start thinking like a true scientist and engineer. This table right here, this is your official lab notebook. We're going to do 3 test runs. For each one, you'll blow up the balloon, let it rip, and then measure how far it went. But don't just write down the number. That's not enough. In the other columns, describe what you saw. Did it spin out? Did a wheel fall off? And the most important question of all, based on what you saw, what one change are you going to make it go farther next time? So, you want to make improvements, but maybe you're not totally sure where to start. No problem at all, we've got your back. Let me give you a few pro tips to help you engineer your racer for maximum distance. Okay, listen up, because these are game changers. First, wheel quality. Wobbly, lopsided wheels create friction, and friction is the enemy of speed. Get them as round as you possibly can. Also, try different wheel sizes. Does bigger work better or smaller? Test it. Then think about aerodynamics. A smooth, sleek body will cut through the air better. And finally, alignment is absolutely crucial. Make sure your wheels point straight ahead and that your balloon's nozzle, your thrust vector, points directly backward. Any little bit it's off to the side is just wasted energy. Okay, you've learned the theory, you've built the machine, you've even started thinking like an engineer. I think it's time for a super quick pop quiz to see how well you've got this whole Newton's third law thing down. Ready? Let's go. First question. Just think about walking. Your foot pushes the floor backward. That's the action. So what's the equal and opposite reaction? What's the force that actually moves you? It's the floor pushing you forward. All right, next question. This one's a classic. A baseball bat smacks into a baseball. Which force is bigger, the bat hitting the ball or the ball hitting the bat? This might feel like a trick question, but it's not. According to Newton's third law, they are exactly the same. The forces are always equal. And for the final question, let's bring it all back home. In your racer, the balloon shoves air backward out of the straw. That's the action. So, what's the reaction force that sends your racer flying forward? It's the air pushing the balloon and your whole racer forward. You got it. Fantastic job on the quiz. Okay, we are now in our final and maybe the most important section. It's time to put on your NASA flight director hat and really analyze the data you collected from your test runs. Let's debrief your mission. Look at your data table. First off, did you get better? Did your distances go up from trial 1 to trial 3? Second, can you pinpoint the one single change that gave you the biggest boost? Was it making the wheels rounder? Changing the body shape? And third, here's the big one. Why do you think it worked? Try to connect it back to the physics. Did you reduce friction? Did you make the thrust more efficient? And finally, what's next? If you had one more chance, one more trial, what new idea would you test? This is exactly what real engineers do every single day. And that's a wrap. You did it. You went from the theory in a textbook to a hands-on build, to testing and analyzing your own data. You've seen with your own two eyes how a simple law, action equals reaction, can launch rockets into space and power your own homemade race cars. So I'll leave you with one last question. You're a rocket engineer now. So, what problem are you going to solve with it next? Thanks for building with me today.